All right. Good morning, everybody. Looks like people are still trickling in and getting a little bit better at setting up these meetings. So hopefully that means there's no people in the waiting room. So that's good. Let me know if for some reason you can't hear me, but we'll get started with today's lecture pretty soon. I have a few announcements. One of them is that and I'll send this in a message as well for all those people that are maybe late and show up a few minutes late. But first one is I did send out instructions on how to, sign into set up your Pearson account, and I also did send the notification that we have the first homework assignment posted now. So hopefully you guys can get a chance to go look at that, start working on it, and just let me know if you have any issues that either I can help you with or that we need to ask somebody for help on. The other thing that I'm gonna ask you guys to do is to go ahead and start your Reef or iClicker app. So we'll be doing a few of those questions today. The other announcement that I wanted to make has to do with, and I will revise the syllabus accordingly, but I'm going to, so I've decided that in terms of participation for this course for the rest of the semester, what I'd like to do is, so it's still going to be that, that 5% that I mentioned, and everybody that joins participates using iClicker, and you log into the live meeting. However, if for some reason you can't make it, or you foresee that you're going to have some difficulty throughout the semester, I would just ask, or in addition to that, if you just think maybe every once in a while, for whatever reason, you just can't make it to class, all you need to do is to just send me a message saying, hey, I can't make it for this reason. If it's a medical reason, I prefer if you could kind of send me a screenshot of like a doctor's note or something. But even if it's something technical, like your connection's horrible that day, or maybe you've got to help out your kid that's in virtual learning and you just can't make it that day, all those things are excusable. And so all I'm asking is just send me a message saying I can't make it for whatever reason. And there won't be any penalty, but I will start deducting points if I don't get any kind of a notification. Does that make sense to everybody?
Good question, Professor.
Yep.
Have you thought more about sharing these OneNote with us? That way it can start being organized, and then even we can add to it questions. And because I'm assuming a lot of us have the same questions.
So you mean sharing it while I'm giving the lecture? Is that what you're saying?
No, like afterwards. So like when we go to do this homework, we can go back to this to see, okay, well, this is what vectors and motion is.
Right.
Just so we have instead of doing our own notes, we have it directly from the teacher, and then we can follow it with the recording if we need to.
Right. I do. So I guess you're the one that suggested it the first time, right?
Yes, sir. Just because I've had teachers in previous universities do that, and we found it very beneficial because the students could even make their own folder then for questions and answers, and a student could ask a question and another student can answer it. And
right.
There's just another way to collaborate since we can't actually be in person with this.
Sure. Okay. So the reason I haven't done it is just because I haven't gotten around to it. But
okay.
Yeah, I'll do that.
And I do know there's a little bit more work for you because then you have to make sure you organize it and label it.
Yeah, that's
so
that's part of it, and a lot of this has been
too of saying, well, I had a lot more work to do because of it, but I do know it did help me a lot. It helped me a lot with my discrete mathematics class because it allowed us to talk to each other and get different perspectives other than just the professors. Sometimes what you say doesn't just click, and then the way a student just explains it just clicks a lot better.
Sure. Okay. Well, that makes really good sense. And I think I'm actually kind of stuck on the fact that you said you took discrete mathematics. What's your major?
Um, this is my second degree. I'm going pre-med now.
Oh,
My
okay.
first degree was in computer engineering, and then the second one was management information systems, and now
Okay.
I'm
Well,
pre-med.
all right. Well, yeah,
I'm
you
old.
said
I'm
it,
like
you
almost
said
31.
enough. I know why you took that class now then. Okay. Um, but no,
I'm old. I'm almost 30.
well, I'm not asking for that, but okay. um, no, but it is, I completely agree. And so yeah, the only thing I just haven't gotten around to is like you said, to just organizing things, because currently some of the notebooks I have are mixed with a few other things that are not physics 1403 related, and I'm getting better at organizing it. But I will. It is going to happen, and it my goal is for it to happen this week. I was more focused on making sure all the other stuff was up and running, like finally we have the Pearson axis, you have the homework axis. We we know how to do Zoom meetings now without too much of a hassle. Um, so yeah, that's definitely on the list of things to do. So put right here, and you guys can all see my screen, right? Hopefully. Anyway, so I'm going to share OneNote files with everybody by this week. So now it's written in virtual stone. All right. Let me just make sure that I am in fact recording. I think I am. All right. Any other questions or suggestions from anybody else in the class?
Just random one. Make sure when you share the notebook, you don't share the whole notebook, because if you have
Right.
other books in there, we're going to see that too. And I don't know what you have in there as far as
Yeah, I'll either
mathematics.
share just I'll probably just share the single notebook for your section of this class. But I'll try to do it right, and you guys can check me and let me know if I did it wrong once I do it. All right. So, what else did I need to mention? Yeah, so like I said, the homework is posted. It's going to be due on Wednesday. If you haven't set up your account, try to work on that today so that you're not rushing. So what you don't want to do is put off till the last minute getting your Pearson account like right before the homework's due. So if you do that, hopefully today, then you'll have a your nice proper week to do the homework. And it's mainly going to be over units, significant figures, motion diagrams, the stuff we talked about in chapter 1. All right. So we're going to go ahead and jump into chapter 2 lectures. So as I mentioned last time, we are using the new set of slides now. And hopefully you've had a chance to look at them and to download them and all that stuff. So one of the topics that we're going to be covering in this chapter is, so we've kind of started describing how, ways to take motion you see with your eyes to creating these motion diagrams. And in this chapter, it's labeled describing motion. And one of the things that we're going to find is there's going to be other quantities that we're going to discover beyond displacement and velocity. And so previously we had already made the description of when we're talking about motion in one direction. We decided we're going to use a number line, and we usually label, which in our positive x-axis is usually to the right. And so when we're talking about horizontal motion, this is going to be the way that we're going to describe it, using a horizontal x-axis. And so similarly, and so if you had an object that had, for example, position x equal to -4, then you'd have your number line. Hopefully it looks nice and straight compared to mine. So that's the 0, then -4 would be somewhere to the left of the line, right? We're going to also be working with vertical motion. And in those cases, we'll use a vertical line, right? That makes sense. And in this case, we'll use the positive y-axis to describe that motion. And similarly, there's always going to be a reference point, which is our 0 point. And so if you had an example of a position that was maybe y equal to 6, then you would end up drawing it on your number line. And that positive 6 would be above the 0, okay? So hopefully that's not too bad of a jump. Now, what we haven't done so far yet is we haven't talked about plotting this kind of data. So we're going to be plotting X versus time graphs or plots. And so in that case, since we are familiar with the motion diagrams already, and the motion diagram, so I'm going to kind of copy the one that's on the slide there. In a standard motion diagram, you might have a situation where you start off at t equals 0, and that has a corresponding position on the x axis. And over time, you see, at least the way that it's shown on the slide, there are corresponding velocity vectors. So remember, these are velocity vectors, the green ones when they plot them that way. And so, and I'm not going to copy the entire thing exactly, but you can see on the set of slides that there's a number of these velocity vectors at different time intervals. And so in that example, it says here that we are using, so between each point is 1 minute. So it's 1 frame per minute. So that means every time you see the dot with a new velocity, 1 minute has elapsed. So if we go and ask the question, okay, well now if we're gonna make a X and time plot, and I use the word plot and graph interchangeably in this class. So you might have, your positive Y and your positive X axis. In this case, when we do X versus time plot, we're putting the X on the vertical axis, and we're putting time, in this case, for this example, since we're dealing with minutes, we'll use time in units of minutes. And so let me actually make the X-axis a little bit larger here, or a little bit longer, I should say, just because I want to plot more of the points that are on the example. So this is time in minutes. And so one of the things that you can see in that graph is if we go from motion diagram to the this XT plot, then at the very first time equals 0, we're at we have some kind of a so we're going to be plotting position. And so on that graph, what you see on the number line is position. So if we're starting off at t equals 0 at x equals 0 here, then on the corresponding graph, we're going to have our dot down at the bottom. And at a later instant in time, it says, so you have one point that's in between the 0 and 100. So if that's 100, you have some kind of a point here somewhere. Actually, hold on, I'm doing this incorrectly. So we have to make sure that we're dealing with minutes on the x-axis, right? So let me, it's a little bit too close here for me. All right, so we'll just put the time down here. So at 1 minute, the first dot in that case, in that graph, tells you, well, we're somewhere between 0 and 100, right? So if you have the value of, let's say 100 is right there, then for that first dot, for the first time instant at 1 minute, we're gonna have something that's below 100, right? So it'll be somewhere kind of down here somewhere. And then you go to the next minute, so time equal to 2 minutes. That's when we're a little bit past 100. So at 2 minutes, we're a little bit past up here. And then at 3 minutes, we start approaching the 200 position mark. So in this case, I'm making way too many lines here, but that'll be the 200. So you get these kind of a plot where all of a sudden when you get close to the 1, 2, the 3, 4, 5, and 6 minutes, we see that suddenly we start to slow down. And the way that shows up in the graph is, well, now when we go from 3 to 4 minutes, you didn't travel as much. When you go from 4 to 5 minutes, you didn't travel as much. So you see that these dots are not changing very much in the y-axis. And then suddenly, once you get to later time, we see that we're covering more and more distance. So now we're at 1, 2, 3, 4, 5, 6. So by the 7th minute, all of a sudden your velocity is bigger, you covered more ground. When you go from the 7th to the 8th minute, you cover even more distance. And so the way that gets reflected on this graph is, well, you can see from 6th to 7th minute, you made a jump. And then from the 8th minute, you also make a nice big jump. And as you keep following in time, you know, you keep covering more and more distance. And so one of the things that you can kind of visualize, you know, just by looking at the thing, you might realize, well, this actually looks like we're tracing almost like a line through all the points, right? Where at the very beginning, that was one line with one kind of a slope. And then there's another interval in time where the slope of your points is a little bit more shallow, right? And I'll just do a dotted line just to kind of help you see that how it's a different slope. And then at the later instant in time, our slope increases again, right? Or it gets even steeper than before. So if you trace a line through those points, you can see that, you know, there's basically 3 different slopes. So in this case, that's the steepest slope. At the very end, we have the steepest slope. And somewhere around the middle, this is where we had a pretty shallow slope. And so just by looking at these slopes of these points, it starts to give you an idea of the fact that maybe you're going a little bit faster, right? So wherever it's shallow, we didn't cover very much of a distance. Wherever the arrows are big for velocity, you covered more distance. So that tells you there's higher velocity when you have a steeper slope. And so you could take any piece of data that is time and position information, and you can plot that. And so the main thing to take away from all this is that when you make these graphs, it's not only giving you information about position and time, but it also gives you information, like I said, we're gonna learn something about velocity here in a little bit. And so essentially when you have a steep slope, that implies that we have a faster speed, or I'll say fast speed. And similarly, if you have a shallow slope or a slope that's not very high, then that implies that we have a slow speed, okay? Now, I'm gonna go ahead and add something a little bit extra here, and that is if the slope is positive, then that means our velocity is positive. And if the slope is negative, so meaning it's pointing down instead of upward as you go in positive time, then a negative slope is going to mean a negative velocity. And remember, velocity not only tells you how fast you're going, but it also tells you the direction. So if it's a negative velocity, it means you're going in the opposite direction to the x-axis. Any questions about that? So we'll be doing a few problems in a bit here. but in this case, those are things that you have to consider. So, you know, when you plot position versus time, slopes tell you about speed, and then if it's negative slope, it's negative speed, positive slope, positive velocity. I meant negative velocity for negative slope, not speed. All right. So in a way, what we just did, we just went from a, so it is possible. So what we observed here at the top is a position versus time graph. And it turned out that it is possible to go from a position versus time graph to a velocity versus time graph. Okay. Well, let me back up just a tiny bit, because this is going to be critical now. I mentioned all these things about slope, but let's just have a little bit of a refresher on what the definition of slope is, right? So slope defined. This is just the stuff you learned in algebra class, where if you want to find out the slope of a graph, it's always going to be, you know, depending on who taught you this topic, they might have said rise over run. And, you know, if English wasn't your first language, you might be like, okay, that sounds weird. Like, what does that even mean, right? But just remember, rise is kind of like the sun rises, right? So that's a positive, that's a vertical direction. And run, well, when you run, usually we run horizontally, right, on the ground. So that really is the x-axis. So slope of a graph, rise over run, tells you how much you're changing in the y direction over how much you're changing in the x direction. If your graph is of positive y and x, in our case, for example, we're dealing with position versus time in this case. So in this case, the slope is always going to be the vertical over the horizontal. So it's, in this case, it would be the vertical over the horizontal, which is time. All right. So I just gave you two examples. In the first example, we were considering a coordinate axis that was plus y on the vertical and plus x on the horizontal. In the next example, and which is here on the right, which is more relevant to our discussion about velocity, well, the vertical is position and the horizontal is time. So it's always going to be vertical over horizontal, all right? So the next topic that we're going to address then is, I don't know why I added this in the wrong place, but hold on just a minute. Okay. It's gonna be annoying. Just a minute here. All right, so what we're gonna do now is we're gonna go from position versus time to velocity versus time. And so in this case, if we start off with our initial position time graph that we had in the previous example, well, we had something that looked like this, where we had, you know, one slope, and then the slope kind of decreased a little bit, and then after some time it increased again. All right. Well, because velocity is this delta x over delta t, which is the slope, then in order to go to a velocity versus time graph, and I guess the other thing that we got to ask at this point is, what are the units we're talking about, right? When we're talking about position, these are units of distance, which is meters. In time, a lot of times we'll deal with, in this example, we're dealing with minutes, so we'll keep minutes. So when you go to a velocity versus time graph, time will still be in minutes, but now velocity, because we're dealing with dividing distance over time, you just gotta remember that the units of velocity are gonna be, in this case, meters per minute, or meters per second, or so meters over some unit of time. And so what we would end up doing in that case is to say, okay, well, we know we have 3 different velocities. So let's just call this velocity 1, velocity 2, and velocity 3. Well, velocity 1, it's a constant velocity over the entire time interval, right? So if we're looking at an interval that goes to about 3 minutes, which is where this kind of inflection occurs. So that's 3 minutes. And then there's another change in slope at 6 minutes happening kind of out here. Then when you make a velocity time graph, where you're going to say, okay, well, there's going to be something that kind of corresponds at 3 minutes and at 6 minutes for this velocity graph. And so we know all these numbers are positive, so they're going to be in the positive velocity axis. And the first one will have some kind of value. In the plot, they actually tell you that it's 1 meter per second. In this case, I'm not too concerned with the actual value yet, but we know we're going to have a value for velocity. And just pay attention to the fact that I just drew a horizontal line. And that makes sense because from 0 to 3 minutes, so from time equals 0 to 3 minutes, we know that it's a constant velocity. So it needs to be a constant value from 0 to 3 when you make the velocity graph. So I'll just label this real quick, velocity graph. The top one was a position graph. So we have a horizontal line. Now, when we go from 3 to 6 minutes, you'll notice it's still positive, but it's a more shallow slope. So now we're gonna have something that kind of like what I'm drawing now. So it's gonna be more shallow, constant value, and there's that. When we get to 6 minutes, you'll see that's where we have the steepest slope, steepest positive number. So similarly, and let me just recap here from 3 to 6 minutes. We have V2 is a constant. And you could even label on the graph here, this is the value V1, this is the value V2. And then from 6 to whatever minutes, I guess in the graph they go to 9 minutes. V3 is also constant. So you expect to have a number that's higher than the other two, and it's a constant value. And this should be a horizontal line because it's a constant velocity, right? Constant slope over this entire time of 9 minutes. So this is your value V3, all right? And a lot of times I'll put some dotted lines in between the values, but really what matters is that you put the V1, V2, V3 in the correct location. Questions so far? All right. Well, let's go ahead and do a little bit of a quick check here. So if you look at the diagram here on the right-hand side, first they show us a motion diagram of a car that's moving along a straight road. And so right away, we can see the position of the x-axis. The x equals 0 position. And we also see the green arrows. And if you remember, the green arrows usually are velocity in this book. So that's a little bit of a hint to help you out. And so what we're supposed to do here is to decide which is the correct velocity versus time graph that matches that motion diagram. So what do you guys think? So remember, we're plotting velocity. And so we have to make sure that the slope is the correct direction. So all those velocities are pointing to the right, which should mean that they're a positive velocity, right? I'll leave this open just so you guys can see. And then after some time after the first kind of 3 arrows, all of a sudden they switch to these longer arrows, which indicate larger velocity. But all 3 of those last arrows are the same size. So that means it's a constant velocity. So when you look at those graphs, you got to find essentially there's going to be two velocities that are constant and one's more positive than the other. And so in this case, the only one that really does that is option C, right? It's a constant, one size, and then all of a sudden it jumps to another size. Now, some people may have wanted to choose some of the other graphs initially. Those graphs are more about position, right? If you can see how initially, if this is, so for example, if we had chosen A, which is the wrong one, actually, let me kind of confirm that. But I know a lot of people maybe chose A initially, or maybe chose B. Well, if you choose A, I could have seen if this had been a position graph, it would be the correct answer, because if instead of velocity, we had position here, then it does kind of make sense that you have one slope at the beginning and then a steeper slope later on, right? But we're talking about velocity. So in this case, constant velocities, all right? Let's see here. All right, so here's another question. Let's see if it's getting you guys in better shape now. So now it's a motion diagram. Once again, green arrows are velocity. The thing that you have to pay attention to in this problem is that, so because the arrows are pointing to the left, we're starting out on the right-hand side, right? So time equals 0 is on the right-hand side here. And so our arrows are pointing in a negative direction, okay? And then after a while, they get even more negative, right? So those negative arrows get larger, but they're still pointing to the left. So in that case, when you look at these graphs, you have to find the one that has basically both values of velocity have to be negative. And then the first one at the initial times, which was less negative, has to come first. So B and D are the only ones that have both of them as negative, but D is the only one that has it first show up as only a little bit negative, and then later on it gets even more negative. So for this one, in fact, as most of you have selected, the correct answer is D, right? Okay, let's do one more, or maybe just one more. So here's another one. It says a graph of position versus time for a basketball player moving down the court appears as follows. So instead of a motion diagram, they've given you now a position graph. I'm going to close that so that not everybody can see what's going on. And so now we got to find the matching velocity graph. So once again, well, let's look at that position. What does it tell us? In the very first, so you can tell there's two segments, right? There's one segment where position is just a horizontal line. And then there's another segment where the position starts to go from a positive values downward towards 0, and then finally towards negative values. If we use information about slope, well, we know the very first part of the motion is just 0 slope, which means 0 velocity. So that's going to be the first hint. And if we consider that, then B and C do that. Okay. So then what? Well, then we have to look at the fact that we do have a slope here, and the slope is negative. So we need to have a negative, and it's a constant value of velocity, right? And so in that case, that helps us narrow down the answer, and it ends up being C. So there's two slopes, one's 0, and then one's negative. Okay? Questions? All right, so now we're gonna go the other way around. So now what we're gonna do is we're gonna say we wanna go from velocity to a position versus time graph. So in this case, they're giving you the velocity, they're giving you the well, okay. That's what I want to talk about, but this particular graph isn't exactly doing that yet. But let's just look at this graph for a moment here. It says here, so they're giving us a position versus time graph. And so, yeah, I'll go ahead and just delete this heading for now. So the first thing that we want to do is they're asking us to draw the velocity versus time graph for this particular problem. And then we want to describe the car's motion. So as I recommend that you make a drawing of the problem and the information. So in this case, we start off with, here's position X versus time in seconds. And we know from 0 to 2 seconds, we have this negative slope that goes down to -4. So that's going to be one part of the motion. And then from 2 to 4 seconds, we have a horizontal line. And then from 4 to 6 seconds, we have a positive slope line that ends up at 6 meters, right? So if I increase this, so that's 4, 5, 6. We have, this is the final point. And so we'll make our graph, our lines kind of go through sort of like that, okay? So the first step, like it says, is to draw the velocity versus time graph. And we're gonna try to draw it with all the correct numbers this time. So in this case, one easy way to do it might be to just draw it here at the bottom. We know we've got negative and positive slopes, so we gotta give enough space in our graph here to include some negative values. So this is now going to be a velocity graph. And because our position graph was in units of meters, our velocity graph, well, since we were in meters and seconds, our velocity graph is going to be meters per second. Remember, rise over run. And then time is going to be in seconds. So for the first part, so we know there's going to be a few distinguishing places. We know at 2 seconds, something's got to change. At 4 seconds, something's got to change, right? And we're going to end up at 6 somewhere. So first question is, okay, well, if we want to draw velocity graph, well, we need to know the velocities, right? So let's do from 0 to 2 seconds first. Well, velocity is going to be delta x over delta time. In this case, we are going to go from, well, we're going from 0 to 2 seconds. So, and I'll just actually spell it out specifically or explicitly here. So it's 2 seconds minus 0 seconds. And so for the corresponding x, we need to find what is the x position at 2. So we go here, our graph at 2 seconds, our x position is -4. So we're going to put -4 up here. Minus the position at time equals 0. So time equals 0, x is also equal to 0. This is 4 meters minus 0 meters. And some of you might be wondering at this point, well, how did you decide which ones to put in what order? And you just have to remember that this expression delta x over delta t is nothing but x final minus x initial divided by t final minus t initial. So this is something we covered previously. So in this case, from 0 to 2 seconds, well, what do we get? Well, we're going to get -4 meters divided by 2 seconds. So that's going to be -2 meters per second. So for our graph here, the first set of points are going to be at -2. So we're going to have this horizontal line up until there. Okay. Well, now let's do the next increment from 2 to 4 seconds. Okay. So now velocity is going to be, as always, delta x over delta t. Our delta t now is from between 4 and 2 seconds, so it's 4 minus 2. These are seconds. And so we're going to do the same thing. We look at our graph and we say, okay, well, at 4 meters, or at 4 seconds, I should say, the position was -4. So put a -4 there. And then at 2 seconds, well, it's still -4. Now, so now we have a situation of, so it's -4 minus -4, so that's a positive. So we have basically 0 over 2, which is 0. And it shouldn't be surprising to you because when you look at the graph, well, that's a horizontal line, which means zero velocity, right? Zero slope is zero velocity. But if you had to go and draw it now on your graph, well, you know you're gonna have from 2 to 4 seconds is just equals 0. Okay, so that's a 0. All right, and then the final thing is, and I'm doing this explicitly just because later on the examples get more complicated, so gotta make sure we're doing it right. So now from 4 to 6 seconds, we do the same thing, delta x over delta t. Our time interval now is from 6 minus 4 seconds. And so once again, we look at position at time equal to 6. Well, we're gonna find that at time equals 6, we're at positive 6 meters. And then minus the initial position. So now the position, the one that counts as initial is the position at time equal 4. And so the position was negative 4. So it's gonna be 6 meters minus negative 4 meters. So in this case, minus negative is a positive, so it's 10 meters. Divided by 6 minus 4 is 2. So 10 divided by 2 gives you 5 meters per second. So when you go and plot this on your velocity graph, well, now we're going to have a value of 5. So it's not to scale, but that's the 5 mark. So from 4 to 6, you're going to have a line that looks like that. And then to make it look pretty, you could put some dotted lines in between the points, but that's not so critical. Okay? Questions? All right. So we just did this problem. So as I mentioned, if we check ourselves, we've got in the first part here, we had our 2 meters per second. Second part, we had 0 meters per second. And the last part was 5 meters per second. So it matches the slides, all right? So the next part is, let's actually read it, the original. It says, describe the car's motion in words. So what is actually going on here? So it basically says at the beginning, we're going -2, so we're going backwards, and then we're stopped, and then we go forwards at 5 meters per second. So what could this be an example of? I mean, so in this case, I mean, this could be something similar, like maybe you start time equals 0 when you were heading out the door this morning. And then at that point you realize, hey, well, I forgot my keys. So guess what? You have to run back. So you might be going back at 2 meters per second. And you don't go too fast because you might trip over some furniture or something. And then you find the keys, maybe they're on a counter, you pick them up. It takes you a couple seconds to pick them up, put them in your pocket. And then you go back the other way. And now you're going 5 meters per second, and hopefully you don't run over things, and you just keep going and get on your car and go to school. So this is an example of a scenario that you could think of, where you'd go backwards and then stop for a bit and then go forwards at a higher speed. Another situation could be what a lot of people do at red lights, right? When the light turns red and people don't stop where they're supposed to, maybe you go over the pedestrian walking signal or walking like stripes. So guess what? You might have to back up a little bit, and then you're stopped for a little while. And then when the light turns green, you kind of slam it and keep going forward. So these are, I mean, potential examples. There's some assumptions I've built into what I just said, but that could be a story you could tell from that graph. All right. So this is the part that I thought we were at earlier. So now the next part is to think in the opposite direction, and we're going to go from velocity to position graphs. So let me go ahead and all right. So in this case, going from velocity to position. So in this case, what's going to happen is we might start off with a velocity graph. So start with velocity graph. And so in the cartoon there, they're giving us something that looks like this. Time is in seconds. And they give you a velocity in meters per second. And the idea is we want to go to position versus time. So in that problem, it tells us that initially we're at 1 meter per second. And it's constant all the way to 15 seconds. So you have something that looks kind of like that. And then between 15 and 20 seconds, our velocity is negative. So it's down here somewhere, -3 meters per second. And so you might have some motion that kind of looks like this. Okay. And so the first thing that we're going to do to build our position versus time graph is we're going to say, okay, well, we have a positive value here. So it's positive 1 meter per second. And that's going to happen for the first 15 seconds. So if I make my line here 15 and 20, well, because we're moving at 1 meter per second and it's positive, but 1 meter per second, well, that means that, you know, so if time, let's just make a little, let's just think about this for a minute. So if time was 1 second, that means we're going to travel a distance of 1 meter, right? So that means at 2 seconds, we will have traveled 2 meters, and so on and so forth, right? At 3 seconds, that's 3 meters. You go down to 15 seconds, we're going to have traveled 15 meters. So that means on this graph, at that 15-second mark, we're going to have traveled 15 meters. And you can add in all the extra points in between. So you could say, well, or you could just add the last one and make your straight line and you're fine. But we could have gone at 5 and put a little 5 right here, and then at 10, and then 10 meters, something like that. So that's the first part. Now, the next part of the motion, 15 to 20, well, so I'll put here V1 is positive 1. Now in this case here, we have a second velocity is -3 meters per second, right? And that's what it says on the graph, -3 meters per second. So now we have a situation where we're decreasing. So because we're decreasing velocity, we're going to be traveling in the negative direction. So, and if we're doing -3 meters per second, and the time step here from 15 to 20, so from 15 to 20 seconds, we're doing -3 meters per second. That's a delta t of 5 seconds. And so each second that goes by, you're going to travel those -3. So, you know, at time equal to 16, you will have traveled -3 meters. At time equal to 17, you will have gone to, your displacement would now be -6. At 18, it'll be -9, and so on and so forth. You can kind of see at 19, and hopefully I did this correctly. You get to like -12, etc. And by the time you get to 20, you're at -15. So that means when you start off from here, you can kind of start adding them. But what I just did for you is I said, okay, in this delta t, when we go from 15 down to 20, we will have traveled -15 meters. So then that means we end up being, so we were initially at position 15, but now between 15 and 20, we have a displacement of -15, right? So you can think of it this way, where our delta x was from 20 meters, from the final position was 0, and then the initial position was 15. So our delta equals negative 15. So we went from a positive 15 down to 0 because we subtracted 15 from the positive 15. So you get this, this graph. And once again, if you look at the slopes, this one's going to be a steeper slope, steeper and negative, to indicate that it is a larger magnitude negative velocity. And the graph on the slides looks a little bit more clear, right? You can see it's kind of shallow and it gets really steep. All right, so now that you guys are all experts at this, so let's do this quick check problem here where you've given a motion diagram and you need to identify what is the correct position versus time graph that matches the motion. So see if you can answer that, see what you think is the best answer. Pay attention to the location of the x equals 0 mark. That could be one source of where you can make a mistake. All right, so let's take a look at how everybody's doing so far. So we got a lot of E's, some E's, and then a bunch of copycats that just chose E because they saw everybody else put E. Not judging, it's okay. So let's take a look and see what's the best way to answer this. So the most common answer is E, and before I showed you guys, there was a little bit more of a spread. But let's take a look at why it might be E. So in this case, when we first start off, the main thing that, so the main goal here for this quick check 2.4 was that, you know, so our goal is to plot our position versus time graph, right? So this is X, and this is time. Well, the first thing is to realize, okay, well, X equals 0. There, on the position time graph, there's stuff before we get to X equals 0, right? So initially, we have a low velocity. So I'm pointing at everything to the left of the X equals 0. We have a certain value of velocity. It's positive, but we're starting off at a negative X value somewhere. So your plot has to begin with X with a negative X value. So having X down here at the bottom, that indicates it's at a negative low position. So time equals 0, we're down here. Next time point, you know, we are closer to X equals 0. So the next time point, we're up here somewhere. And then the very next time point, we're also a little bit closer to 0. So we might be kind of up here somewhere. And then at some point, what happens at this point? Once we get to X equals 0, so far we've traced this line. Well, now the arrows got bigger, right? The arrows got bigger, which means higher velocity, which means larger slope. And so your graph is going to have a larger slope at later times. So it was shallow slope, negative values. Once you get to X equals 0, velocity increases and you have a positive slope. So in this case, that's why we ended up with our choice of E for the answer. You can tell for D, it's the same shape, but we're not starting at negative X values. If in the motion diagram that X equals 0 was all the way to the left on the very first time point, then you could say it was D. But in this case, because there's negative values, we choose E as an elephant. All right, let's do some more of these. There's a reason for doing these, and it's because you just have to be able to switch back and forth quickly. So in this example, they give you a graph of velocity versus time for a hockey puck shot into a goal. And it appears as follows. So you have velocity. So the idea here is they're giving us a velocity, and now we want to find the position graph. So what's the best way to go about this one? We have, so you have to look at really the slopes to tell you anything about, if things are changing. So let me start a new slide here. So in this case, I'll just draw the velocity versus time graph real quick. Looks like that. So the idea here is to get position. Well, initially, so we know there's going to be something happening at the middle of our graph. Something's going to change. But initially, we're moving at a constant positive velocity. So that means we need to have a constant positive slope in our position versus time graph. This is the position graph. That's the velocity graph. So what do you think that'll look like? Well, it must mean that we have some kind of a slope that goes with it, right? All right, so far we got B and D. That might be a candidate. And then what happens after that? After that constant slope, we go to velocity of 0. So initially, we're moving with a constant positive velocity. And the next part, velocity is equal to 0. Well, if velocity is equal to 0, means you're not moving. So position should not change. So no change in position means, well, if we were up here and all of a sudden we're at 0, well, we're just going to stay at this X value. Kind of like that. So in this example, the correct answer was D. And if you think about the word problem, it says this makes sense because it says we're plotting the velocity versus time of a hockey puck that got shot into the goal. So let's say that the puck got shot from the middle of the court. It goes from the middle of the court to the glove. Okay, that makes sense. That we start off at one position. So the position of the middle of the court is at X equals 0. The position of the glove is whatever X is equal to at that point there. We can call this X1 just for fun as a make-believe number. But then because it gets caught, it stops moving, right? So it makes sense that it's gonna stay in the same spot. If you chose B, B is an interesting one because what that says is that the moment that they caught the puck, it somehow automatically went to the center of the court. That's what this one is telling you, option B. Is telling you it was caught and then instantaneously it transported itself to the center of the court and then it's at X equals 0 for the rest of time. But we know that's not the case. It has to stay put, so option's D, all right? All right, let's see here. Yeah, let's do this one. So this one's getting a little bit more interesting. Now you have to think about slopes a little bit more. So in this problem, it says which velocity versus time graph goes with this position graph. So what do you guys think? So we were giving the position graph is in the top corner, in the top right, and we need to find velocity from this. So I'll take a look at your responses in a second here. All right, we got a little bit of a spread between C and D. So what's the best way to think about this? Well, if we start off with X versus time, and it kind of has this thing that looks kind of like a little bit straight-ish, and then it curves, and it kind of just goes straight. All right, well, if we look at the slopes, we know initially this has some kind of a positive slope, and it's slowly going to change to smaller and smaller slopes until finally it looks like it approaches like a 0 slope. So V approximately equals 0. And here V is the highest at the beginning, right? So that's really what we're looking for. And these are all, they're gonna be numbers that vary from positive to 0 values, basically, of slope. So remember, slope really is equal to V. So if we look at V, which is now meters per second versus time, then we need to find a graph that does exactly that. So anything that has a negative value is not gonna work. And I know that I actually did draw it incorrectly, but it turns out it's not even gonna matter. So the correct graph actually does start with negative X values down here. But what matters is the slopes. You still have the highest here. They start to go less and less positive until they get to 0. That's really what we're looking for. So A has negative values of velocity. That's not good because we don't have any negative slopes. And for the same reason, D is out. So then we have B and C. But we already said we have to start off with a high slope, which means a high velocity. And then we're eventually going to get to a 0 velocity at later times. So for that reason, option C is the correct answer. Okay, questions? All right. So we're going to continue on, and we're going to discuss a little bit more uniform motion. We discussed a little bit about how uniform motion, we defined it in one of the previous lectures as motion that is in a straight line and with a constant velocity. Okay, that's what we mean when we say uniform motion in this chapter. So let me just kind of define it here. Uniform motion is motion that is in a straight line, and it is motion that has a constant velocity. So that means that if you're going to make a graph of the position versus time, then that means that the velocity needs to be, because it has to be constant, we have to have a straight line, a straight slope in our line of uniform of x versus t. And the main reason for that is because otherwise it's not uniform. So if we have x versus time, as long as this line is straight, any little section, let's say I want to investigate my velocity in this interval here. Well, at this location, this delta t is going to have a corresponding delta x, which will give you the velocity is equal to delta x over delta t. And so let's just say we're looking at this first time interval, which is called delta t1 and delta x1. Well, later on, when you have uniform motion at another instant, well, you're going to have another little delta t here and another little delta x up here. So if this is delta t2, delta x2, well, you're going to have the same value for velocity up at the top. So if v1 was delta x1 over delta t1, then and v2 is delta x2 over delta t2, then when you have uniform motion, that means v1 is equal to v2. I mean, this is just a more mathy way of saying the same thing. All right, so the reason why we're studying this is because it's gonna give rise to one of our first equations of motion. So I'm gonna write here first equation of motion. And later on, we're gonna find that there's gonna be other equations of motion once we introduce a few other concepts. But in this case, as I said to you, we have velocity is delta x over delta t, which is the same thing as x final minus x initial over our delta t. And so you can use this expression to solve for your change in position or your final position. So for example, you could solve for x final. In that case, you're going to take this delta t and multiply times v. So you have x final minus x initial is equal to v times delta t. And then finally, you can say, well, my final position is just x initial plus v times delta t. And so this is mainly what we're going to use for a lot of problems when we have constant uniform, motion. Another way of writing the same problem is you could just say that delta x is equal to v times delta t. When you write it this way, it's kind of nice because you can see how delta x is proportional to delta t, right? So depending on your speed, you just take your time and you multiply times the speed and you get the distance, automatically here right away. All right, so this next slide is more to teach about relationships between the shapes of curves. So in the previous example, we saw a linear curve. So that linear curve is related to this linear relationship that's delta x is equal to v times delta t. And when I say linear, I just mean that it's directly proportional. You just take a constant. In this case, the constant is v. I'll label that. V is constant. And just remember this, everything that I'm saying right now, it only applies when we're talking about uniform motion. Okay, this is specific to this, and later on we're gonna have motion that's not uniform. And so don't confuse what I'm talking about here with other stuff later. And so this next slide is kind of trying to teach about other relationships. So instead of just being a constant times delta t, you might have equations that are quadratic, that depend on the second power of your variable. And in those cases, you're gonna end up having to square the values. But we'll focus that a little bit more when we actually have problems that have things raised to the second power. But the nice thing about these things when they're proportional is you can set up ratios. And I'll let you kind of look through this a little bit better. I think there's a homework problem that gets you to practice this stuff a little bit more. But it is important to understand this idea of that when they're proportional, you can set up equations kind of like what we started doing up here with our delta x1 and delta t1. All of what these slides are saying is that you can take your expressions and set them up as delta x1 over delta t1 is equal to delta x2 over delta t2. And you can solve problems that way as well. All right, so let's do a quick check here. So here we have a position graph of an object. And it says here, at time equal to 1.5 seconds, what is the object's velocity? So you have options of 40, 20, 10, -10, none of the above. So what do you guys think? How do we do this one? So if you think you know how to do it, put your answer without cheating and looking at the next slide. And so far, we got a split between B and C. I like it when that happens. So let's talk about that, especially since we're still trying to figure it out here. So we have, in this case, all the action really happens between 1 second and 4 seconds, right? That's everything else is kind of 0. So between 1 and 2, we get this increase that goes up to 20, right there. And then after that, from 2 to 4, it goes all the way down to 0. So it looks kind of like, well, if I could draw straight lines, it would look kind of like that, all right? So I like this because you guys chose, so is it B or C? Those are the common answers when I checked right now. And they still are, which is great. So we're trying to find velocity, right? So we know velocity is delta x over delta t. That's the first part. Now you might see the 20 and you're like, oh, well, we went from 0 to 20. So you might be tempted to say like, oh, it's 20, done. And that's not quite true. you do have to think about this a little bit more because so we did go from 0 to 20, that's 20 meters. That's our delta X. But you do have to double check yourself and say, okay, well, what is the delta T I'm talking about right now? Well, the delta T, so they're asking for this at 1.5 second, which is here in between the two. However, the slope at 1.5 second is the same as the slope at 1.1 second. It's the same as the slope at 1.9 seconds. Everywhere in this interval, it's exactly the same slope. So what you can do is you can take this entire line segment here to calculate your velocity. So in that case, your delta T is going to be 1 second, right? We're going from 2 seconds as a final minus 1 second, right? So that's going to give you 1 second. So in this case, yeah, it does make sense that V is going to be 2 meters divided by 1 meter, which, 1 second, which is 20 meters per second. And so in that case, some people had chosen that it was 10. And I think in that case, maybe you were tripped up a little bit. Maybe you thought like, oh, delta T was like maybe 1.5 minus 1 or something to give you something that equals 0.5. But that would give you a big number. The other possibility is you could have gone and said like, oh, well, maybe my delta T is 2 seconds, right? Because I'm just reading the value at the tip, it says 2 seconds. But the problem here is you're doing 2 seconds minus 0. But our line is not increasing from 0. If it was increasing from 0 to 2, then you'd be correct and to say delta T is equal to 2 seconds. However, it's only changing from 1 to 2 seconds. So the time interval to help us calculate our slope is going to be from 1 to 2 seconds. All right. And so I think that's why a lot of people maybe chose C, the 10 meter per second, because they thought it was maybe 2 seconds, but these are all incorrect. All right. So that's wrong. Okay. Any questions? All right. So let's see. Do we have, I think we might have a little bit of time for this one. Yeah, let's do this real quick and then I'll let you guys go. Actually, you know what? We'll do this next time. I want to make sure that I talk about it right and I don't want to rush to the next appointment I've got. So I think we'll stop for there and we'll continue from this point on next lecture. My goal is to get through a lot of the next the chapter and next lecture and maybe just finish it off on next Monday. So if you want to be proactive, just look through all the slides here for chapter 2 and try to get acquainted with everything. Any final questions? And I will work on getting these notes to you guys as soon as I'm able to. But if there's no more questions, then we'll go ahead and stop there, guys. All right. All right, then. So as always, I'll try to get these things posted, the video posted at least hopefully early today. All right. All right, everybody. Well, you have a great day and I'll talk to you later if there's no more questions. Bye-bye.
Hi, I have a question.
I knew it. What's up?
When will our first exam be?
So I will put a tentative schedule up also shortly, but the first exam is going to be until like middle of October. So we're going to go through the first 5 chapters before you have your first midterm. All right. So it'll be mid-October right now is my estimate for you, but I'll share with that.
Do you provide a review for the exam?
Yes, there will be a review for the exam. I can even share this quickly for you guys just so you can look at it, but I'll post this on Blackboard soon. But yeah, so this is my tentative kind of plan. So right here, midterm shows up, actually more like the beginning of October. So I have a review session, the meeting before that, which means I'll distribute a review material like the week before or 2 weeks before. So probably on the end of September, I'll give you a review document to help you prepare for the exam, all right?
And then you had mentioned earlier that if we weren't able to make the class or we're having connectivity issues,
Yeah.
you said to message you. Do you mean like just send out an email?
For now, that's the plan. Yeah, just send me an email. I haven't thought of a fancier way of doing it.
That's okay.
If I do, I'll let you guys know about it. But for now, if you can't make it for whatever reason, just send me an email and you'll be excused.
Okay, thank you.
All right? Sure.
For the homework, do we only have to do the first assignment and not both? Because I saw that we have 2 of them.
Right. So one of the things that and I didn't mention this, so automatically there's these 2 things that show up. One's called like, it's like introduction type stuff. The one that you really need to worry about is the one that actually says chapter 1 homework. Does that make sense?
Yes,
Okay.
thank you.
Yeah, okay, cool. All right, anything else? All right then, guys. Well, you have a great day. Thank you.